what we are now going to do, without further ado, is prove the theorem for which this whole thing was a lemma. The theorem which sort of like completely characterizes any finite projective plane. And here is what it says. We're on the top of page, what is this page? 6, 8? Whoa, this packet keeps getting longer and longer. Alright, so take any integer n greater than or equal to 2. The following are equivalent. One, there exists a line with, can I just be a little casual with my verbs? Can I just say like with? N plus 1 points. Please interpret that as exactly. Good. 2. There is, or there exists, a point that is on a point on exactly n plus 1 lines. Okay. 3. Every line contains n plus 1 points. And the dual of statement 3 is statement 4. Every point is on exactly n plus 1 lines. And then finally, and we kind of talked about this yesterday, that implies somehow that there are n squared plus n plus 1 points exactly in this model. And that there are n squared plus n plus 1 lines. And so somehow, if you give me any n is greater than or equal to 2. So you give me any n of like 2, 3, 4, 5, whatever, and the following are all equivalent. Now actually, this is a little bit interesting because this doesn't say that for any n there exists a model. But I think that just is true. Hold on, let me think about that for a second.
Wait, didn't you say something about n having to be a square?
Not. Yeah, I think n doesn't have to be, I'm doubting myself suddenly for a second. I think that I'm gonna just not say anything and it'll come to me later. Alright, so let's go. Here's what we have to show, the equivalency of all of these. And we're going to be kind of careful about this. I'm going to sort of chart our logical progress here in some sort of like flow chart. So here's 1, 2, 3, 4, 5, 6. Now it's quite a bold thing to show that the following are all equivalent. Depending on how many advanced math courses you've taken recently, this is the kind of thing you do all the time. Who took like linear algebra? Did anyone here take linear algebra last year? So like real linear algebra? No. Okay. Even in some of those people did. Even if you're taking this year's version of linear algebra, you still have like, it's a very common thing, right? To have like a whole long list of statements and to show that these are all equivalent to each other. And there are many ways to do this. Well, we did this in this class even. But the simplest way is to just show that 1 implies 2, which implies 3, which implies 4, which implies 5, which implies 6, etc., right? All in a big circle. Yo, we're doing the finite projective plane. What are you doing? Cool. You need something?
No.
Cool.
I just like sliding.
Woo! Alright, so let's go. This is a little bit more complicated than that because we have these kind of like duality relations. Let's just start. I think I'm pretty prepared for this class. Let's see. What order should we do this in? Do you want to just start or do you want to do like the sort of preparatory work? Let's do the preparatory work. Okay, prep. Alright. Fortunately, the prep we have already done in previous classes and previous videos. So I shall not rigorously go through all the tedium again, but like, let's just talk it out, man. What we have is this beautiful axiom, FPP3. And what FPP3 says is that we have these core 4 points, all distinct, no 3 of which are collinear. We have P1, P2, P3, P4, all distinct, no 3 of which are collinear. All right, and so like I'm just gonna now invoke see video 1 from this series by previously proven steps. We know that like you just get these 6 lines, man. We have 6 lines, all distinct, L1, L2, L3. All right. Note that the one person who was allowed to leave the room left already. My previous group actually has 6 lines, L1 through L6, all distinct. And now I'm just going to kind of just bust out a picture, all right? So here we go. We have these 4 points. And we have these 4 lines, L1, L2, L3, L4, L5, and L6. And this is P1. This, yeah, I just intend for this all to be like done like on the prep work we're going to do on page 8. P1, P2. This is P3, and this is P4. Okay, and all right. Also, so remember how we like did that on the very first day of this unit? Remember how we went through and we very carefully showed that like, you know, your eyes do not deceive you. All these lines are distinct. None of the points that aren't depicted as being on the lines are in fact on the lines, etc., etc. Can you nod with me? Good, so we don't have to do that again. And we also know, since any 2 lines meet, that L1 and L2 meet somewhere. Let's call that point X. Just why not? So change my mind. I apparently have called it. Well, I've called it different things in different places on my pad. Let's not call it that. Let's call it Y. Alright, so L1 and L2 meet at a point Y, and also, and that Y is like different from all the other points. That's another thing that we proved. That L3 and L4 meet at Z. And that L5 and L6 meet at X. And so I'll call that point X right there. And let's see, what else do I need? And then I'll just state more things that we've previously proven. All 7 of these points are distinct. And there are no other incidences. Okay. There are no other incidences. So incidences is like the general term for like a point being on a line or a line going through a point. So what I mean by that is, which we also did all out on the first day, that like, you know, trust your eyes, man. Like X, Y, and Z are all different from P1, P2, P3, and P4. L1 and L2 go through Y, but like Y is not on L5, for example. Y is not on L6. In general, for all of these objects shown, like they don't meet in any more places than the ones we've already pictured. Cool? Okay. And the only thing I really need, so just like note also, the only thing I'm really going to use is that there is this point X, which is not on L1, and X is also not on L2. Okay. And what I would like to say is, from FPP3 and FPP1 and FPP2 alone, like some kind of arrangement like this must exist at the heart of every model of the finite projective plane axioms, right? Let's call this a like substructure or something like that, because this is not a complete model of the axioms, but it's like a substructure like this must exist by virtue of just following the axioms. And in fact, what could I add to make it a model of the axioms? Yeah, yup. If I simply draw a line through x, y, and z, then that just is the final plane. Yeah? So the sort of minimum way to add to this structure to get something which satisfies the axioms is to just add a line through x, y, and z. Because we have already 6 lines here and 7 points, we just add that 7th line, we're done. Okay? But, of course, this might not be the final plane. It might be, because we want everything we're doing today to apply to all possible finite projective planes, including ones in which there are like 100 points per line, right? So in fact, the actual structure of the model might be very complicated. But at the heart of the model, there must exist, by virtue of FPP3, some structure that looks like this. All right, are we good? Woo, okay. So, we begin. Can someone erase that backboard? And I shall now show that 1 implies 2. I was worried that we weren't going to have enough to do today. Show that 1 implies 2. Yo.
Why did you choose to say x is not an L1 or x is not an L2 and not say anything about like L3 and L4?
And just preview, this is the only sort of real fact that I'm going to use, just because, like, but you don't have to understand that comment now. Alright, let's show that 1 implies 2. Okay, so this is actually, should we sort of reflect upon like why this is a pretty amazing overall theorem? Somehow we're going to conclude, just from that there exists a line with n plus 1 points, that in fact every line contains n plus 1 points. In other words, this sort of suggests that like our finite projective plane models are like extremely symmetric and like highly structured, right? Alright, so first of all, why does 1 imply 2? Well, so we have a line with n plus 1 points. What would you like to call it? Yeah, great idea. So suppose L has exactly n plus 1 distinct points. Woo. Well, here's my line L, and here are my points that are on it. P1, P2, P3, Pn plus 1. What do I need to show? I need to show that there exists a point which is on exactly n plus 1 lines. Thoughts? Take a point that's just like not on L. Okay, and there's always a point. It's probably like another theorem that we should have proven. We probably like did-ish. But you can't have all the points on just one line, man. Why can you not have all the points on just one line? I'm pretty sure we did talk about this. But if every single point were on just one line, then that would be just a violation of FPP3, right? Because FPP3 says there exist these core 4 points, no 3 of which are collinear. So you certainly can't have all your points being collinear. Therefore, you can't have all the points being on one line. Therefore, given any line, there's always a point that's off of it. Are you with me? Woo! Energy level in this class is kind of low, people watching at home, because there's a lot of people on field trips. Yeah. That means I'll just pump up the crazy a little bit more than usual. So take this point P, which is not on L. Take point P not on L, and now simply apply the lemma. So by lemma, which one is it? I already have forgotten. By one of the lemma 8.4s. I guess it's like we erased the. It's A, right? Ah. By lemma 8.4a, like there are n plus 1 points, lines rather, through P. Woo! Check. We have shown that 1 implies 2. The existence of a line with n plus 1 points implies that there is some point with n plus 1 lines through it. Good? Alright, good. And then, of course, the fact that 2 implies 1 is exactly analogous. now we take a point which is on exactly n plus 1 lines. So suppose there are n plus 1 lines through P. Well, there must be some line that doesn't go through P. Because not every line can go through P. Because if every single line goes through P, then we have a violation of FPP3 prime. FPP3 prime says there's a core 4 lines, no 3 of which meet at a point. Therefore, you cannot ever have all the lines meeting at a point. So all the lines can't go through P. So there must be some line L that doesn't go through P. So take some L such that P is not on L. And now, by lemma 8.4b, that's exactly what lemma 8.4b gets us, right? There are n plus 1 points on L. Okay, so, good. If there's a point somewhere with n plus 1 lines going through it, and there's a line somewhere with n plus 1 points on it. Alright, so we have now shown that 2 implies 1. Okay, now comes the hardest step of the proof. So we go back over here to this board. The hardest step of the proof is to show that 1 implies 3. Please turn to the next page and edit that top of your packet a little bit, because really, properly speaking, this is really a proof that 1 implies 3. All right, are you ready? Say ready.
Ready.
Woo! Good. So, what is the proof that 1 implies 3? What we need to show is that just from the existence of a line with n plus 1 points on it, that every line must have n plus 1 points on it, showing the sort of symmetry of the overall system. Okay. All right, well, let's begin. Suppose 1, which is to say that there exists a line L, L with exactly n plus 1 points. Okay. All right. Here's where we get into our super high levels of abstraction again, because the argument needs to go in different directions depending on whether L is one of the core 4 lines or not. And I don't want to deal with that because it's annoying. So what we have to do is we have to pull this move where we're okay, there are these core 4 points, P1, P2, P3, and P4. This line L, well, let me just write it down first. Okay, since no 3 of P1, P2, P3, and P4 are collinear, that's built right into FPP3, that there are these 4 core points, no 3 of which are collinear, then this line L, then this line L can intersect at most 2 of these points. Okay. So, without loss of generality, let P1 not be on L and P2 not be on L. Alright, this is really hard, but we did something like this before, so maybe it's getting a little bit easier. what makes this hard is it's like, do you sort of feel why this is so difficult? Right, I have this line L, right? I want it to be totally generic. If it were not one of the core 4 lines, great. But maybe it is one of the core 4 lines. Ugh, it sounds like we have to do all kinds of terrible casework and stuff like that. But no, we don't, because we just retreat to some high level of abstraction and we say, okay, look man, L might be one of the core 4 lines, it might not be. But what I can say for sure about this line L is that though it may go through my 4 core points, it can go through 2 of them at most, right? And if it goes through 2 of them at most, then it definitely doesn't go through 2 of them. So now without lots of generality, let P1 and P2 be the 2 points that the line doesn't go through. Okay, therefore I leave open whether, so what could, looking back at the picture over there, what could my line L be? It could, no, it can't be, wait a second. No, he's right, it could be L2, right? It just has to be any line that doesn't go through P1 or P2. So it could be L2, it could be, that's the only one shown that it could be, right? It could be L2, or it could be some other random line like far away that just, all we know about this line is that it doesn't go through P1 and P2. Cool? Okay. And that's enough for me. Anyone have any questions about that? Marie?
Well, what does it mean that it could be another line that goes through, like is there another line that goes through P1 and P2 that isn't L1? Like, what do you mean?
Wait, I think either I said it wrong or you did. What,
no, not in that example. Just like you said, it could be any other line. But what do you mean by that? Like, what other line? If any other line goes through any 2 of those points, isn't it just like one of those lines?
Yes. What I'm saying is my line L, this line L that I've begun with, any line, let me put it this way, any line whatsoever misses at least 2 of the core 4 points. That's all. That's all this is. Maybe it's not that hard, right? So without loss of generality, let our generic line L miss P1 and P2. And I just simply don't care whether this line goes through P3 or P4 or whatever. Okay, good. All right, so what does my picture look like? I can finally start to draw my picture because I know that I have this line L and I know that it doesn't go through P1 or P2. Okay, so what are my sort of facts that I now invoke? Well, I have these points P1 and P2. They're certainly distinct. Also, L. So L, I'm not even going to draw L. I'm just going to sort of reproduce the relevant portions of the picture from the front board. So I have, here's P1 and P2, and here's my line L2. And then we also have this point X. And what do we know about this point X? We know that it's not on L1 and it's not on L2. So my facts, which I repeat from the front board, is that I have these 2 points P1 and P2 that are definitely different. I also have that X is not P1, that X is not P2, that P1 is not on L2, that P2 is not on L2, and that X is not on L1, and that X is not on L2. And then just like my actual line L, like not shown. Okay. Whew. Good. Everyone okay so far? I haven't really done anything yet. Good, yes, shrug is the appropriate response there. Okay, and now I begin the sort of argument. Claim. Every line must contain n+1 points. Every line must contain n+1 points. Exactly. Okay, why? Well, L has n+1 points, and P1 and P2 are not on L. So, what I now want to do is invoke lemma. Which one is it? I've already forgotten. Okay, so I'll just write it, right? Since L has exactly n plus 1 points, and P1 is not on L, what can I claim about P1?
Oh, it has
N plus 1 lines through it. So now I will sort of, maybe it is it helpful to maybe just kind of redraw this every time, right? I know I have my n plus 1 points on L. That's the original assumption for this part 1, right? And so by whichever lemma it is, lemma 8.4, it must be A. I think it's A. Tell me if I'm wrong. There are exactly, it's B?
I thought so.
They've now fused in my brain.
That's
By lemma 8.4a, there are exactly n plus 1 lines through P1. Agreed? Similarly, since, well, it's just the exact same statement, right? Since L has exactly n plus 1 points and P2 is not on L, then again there's this kind of picture in which L has n plus 1 points on it. P2 is not on L. Again, by the exact same lemma, by lemma 8.4a, there are exactly n plus 1 lines through P2. Alright, so I'm gonna start this notation, I guess. I've just decided I'm gonna do this right now. I'm just gonna go like this, like cha 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 cha. That indicates that we have proven that there are n plus 1 lines through P1. Cool? And cha 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 cha. That there are n plus 1 lines through P2. Good? This is by virtue of there being n plus 1 lines on L. Points on L. Okay. Well now, take some new line M. So now now I'm sort of going to prove that every line has n plus 1 points on it. Alright, take some line M. Take some line M. Why must M have exactly n plus 1 points? Well, there are some sort of cases, right? First, let's suppose that P1 is not on M. Well, if P1 is not on M, then what can I say about M? M has n plus 1 points, because you just have to sort of imagine this line M just chilling here, right? Not going through P1. Well then, all of these n plus 1 attack lines coming out of P1 just kill it in n plus 1 places. Good. Whew. Adding active verbs for excitement. Alright, so if P1 is not on M, then this must be lemma 8.4b. By lemma 8.4b, there are exactly n plus 1 points on M. Alright, that's pretty easy. In other words, I'm trying to show that every line has n plus 1 points. Well, for starters, any line that doesn't go through P1 must. Agree? Okay. Are we cool?
Yeah.
Whew. Okay, now, next. What if, on the other hand, what if P2 is not on M? Well, it's in the exact same thing, right? If by lemma 8.4b, if M misses P2, then the n plus 1 lines coming out of P2 must meet M. So then we conclude that there are exactly n plus 1 points on M. Okay, so yes.
Unless M is like L1.
Yeah.
Like it's fun, but.
Yes. Yes. Alana is exactly correct, right? What are the category of lines we have dealt with now? We've dealt with all the lines that miss P1. We've dealt with all the lines that miss P2. What's left? The lines that don't miss L1 and don't miss L2, which is to say.
I think you mean P.
Am I saying it backwards?
You said L1 and L2.
And I did mean P. Strike the last 20 seconds from the record. We're trying to show that every line has n plus 1 points on it. We proved it for all the lines that don't go through P1. We proved it for all the lines that don't go through P2. So the only thing that doesn't fall into either of those categories is the line that does go through P1 and P2. In other words, L1. How do I write that down more clearly? I have some crap on my paper. Let's see. I'll just write some suggestive questions. What if neither of those is true, right? What if it's like not the case that P1 is on M, or is that what I want to say? Yeah. Or P2 is on M, or P2 is not on M. Well, then that's just saying that P1 is on M and P2 is on M. In other words, the only case left is the case in which line M goes through P1 and P2. But if line M goes through P1 and P2, then it just is L1. Okay, so now just repeating myself, L1 is the only line left to deal with. Who is with me? Basically, good. All right, how are we going to show that L1 has exactly n plus 1 points? If I can do this, we're done. Show L1 has exactly n plus 1 points.
Can I snag another line from there?
Yeah, sure.
Alright, if we bring in L3, we know L3 has n plus 1 points on it, so X has n plus 1 lines through it, so L1 has n plus 1 points on it.
Yeah, that's pretty much it. Though I think, is what you have done good enough? I bet it is. I bet it's nicer somehow, though, to have, I guess it doesn't matter. I was going to do exactly what you said, but to do it with L2. Because
it does miss both.
I think it does. I think that it does matter, right? But yeah, he's exactly right, right? To show that L1 has exactly n plus 1 points, well, take another line that's not L1, right? We have already